So this is the start of a Julia triple header. Jeff and Stefan are back there and will speak after I do. This is going to be a talk about climate change and Julia. And yesterday, as you could see in this picture, we were walking around amongst the antiquities. I was thinking about 2,500 years. I don't think anyone ever expects any programming language to last 2,500 years, not even Fortran, I think. Fortran, 25, never mind. I don't see that happening. We actually now, with issues of the climate, we even have some worries about the human race lasting another 2,500 years. We certainly hope that will happen. So let me tell you a little quickly about, the story of this talk, or basically why am I here? So I don't have to tell this group that programming languages make a huge impact. You already know that. But I want to tell you about some of the work that I've been doing, or the Julia Lab, or some of the stuff's happening at Julia Computing as well. But some of the things that are going on in sort of my corner of the Julia world, if you will. And so some of the things that I've been involved with now are sort of big climate models. So these are big high-performance computing problems. And so we're getting into more and more now applying Julia high-performance computing. Differentiable programming is a big deal, and scientific machine learning. And so I thought I would tell you about some of these things. But really, the actual thing that happened, and it's kind of a bit of a sort of funny connection of things that happened, my two colleagues, Ron Rivest and Michael, who's right here, Ron asked me, he was looking for somebody in computer science to talk about the climate. And I happened to be involved, and so I gave a talk at one of the computer science retreats at MIT, and Michael was there, and I also talked about differentiable programming and was invited to come talk here in Athens, and I'm happy to be here. This is my first time here. So to start with climate a little bit, unless you've been living under a rock, you probably sort of know the basic story. The sun is heating the earth, and the energy from the sun is not escaping as fast as it would if we didn't have the greenhouse gases. This was well understood by Fourier himself long before computers were as we know them today, or arguably not even invented yet at all. So the concept of you don't need big climate models to understand that if CO2 is being trapped in the atmosphere and it's not going away anytime soon, the Earth will heat up. Okay, we don't need climate models for that. Maybe the question of exactly how many degrees, depending on whether we change our habits or not, is a much more complicated question. But the fact that the Earth is warming is completely agreed upon by nearly all scientists today. Okay, and so some of the effects, here's Boston. For those of you who know Boston, seeing it underwater might be scary. We made I asked my son to make a little cartoon to be able to sort of make an impact to the computer scientist at MIT. And so this here is the computer science building. And as the ice melts, the polar ice caps melt, water will rise. And that I'm told by my colleagues in the Earth and Atmospheric Planetary Science group that this is going to happen. It's probably not going to be quite as dramatic as the 9th floor of the computer science building, but it will happen. So a couple of news articles before we delve into the technology. So I'd like to tell you a little story about how I got involved with this, because I hadn't been a climate person at all until last fall. So what happened is at MIT it's called EAPS, the Earth and Planetary Science, Earth, Atmosphere, and Planetary Science group. Some of the faculty from EAPS came knocking on my door over in Stata, literally right next door to Michael's office, and they said, don't talk us out of it. We want to get rid of our old Fortran models. We're going to rewrite all of our code. We don't want to use legacy code anymore. It won't work. Right? That was very refreshing. I'd never heard that before. And don't talk us out of it. We want to use Julia. Like, okay, great. And then they said, but we need to convince some other people. So we'll give you, we have a little test. We want your group to help us out with this. We heard that writing in Julia is going to make the science look like the math instead of sort of ugly code. So we really like that idea. But we're very worried about performance. So we're going to give you a little test. They gave us a little code, and they said that if you can make this code work within the next 3 weeks, and we'll give you like a factor of 3. If it's a factor of 3 slower, it's okay. We'll take that factor of 3 slower to have really nice code. So we did this, and a couple of weeks later, we go back to them and said, we got you that factor of 3. It's 3 times faster. So fast forward to this semester, and there's a class today that I'm missing because I'm here. Ron Rivest had asked me to help out with a climate change seminar for computer science students, which was quite interesting. One of the things that I learned was that the needs and interests of computer science are completely different from what you would find in other parts of MIT, like at EAPS or other places. Computer science students really do care about the environment, and they really want to do something, and they're trying to figure out how they can help, and so it's quite a lot of fun to work with these students. Okay, but the class, by the way, is not completely about climate change. It's about the entire issues of problems involving the climate change. So economics, the mitigation, it's a long story. But getting to the part that I've been involved with, the climate change simulation, there are a lot of challenges involving discretization. The big Earth gets discretized into little small pieces, and if you really want to understand the actual physics of what's going on the Earth, you really have to discretize down at a sort of very local level, which means a lot of computation, basically more computation than computers can really deal with today. And so people are pushing the limits on that. There are a lot of computer science problems. There are a lot of what are so-called computational science problems where the applied math comes in, and the issues of programming high-performance computers, because this sort of old ways of programming HPC is just not going to really cut it. And so as this slide says, I've been living in the HPC world for a while, and if you've ever looked into this world, you find out that things really haven't changed enough, in my opinion, over many, many years. There's been a lack of portability. This is becoming a bit of a crisis because now everybody wants to run on GPUs and on other kinds of architectures, and nothing works anymore. Reproducible science is kind of unheard of in that community almost. I mean, things are changing, and there's a little bit of it. But there are all these climate change models, for example, and I just asked the people, if I wanted to run any one of them, can I? Like, is any of the code on GitHub? Can you email me the code? And people would say to me, oh, well, you're going to need a fancy computer to be able to run it. It's like, fine, I'll get one. Now, can I get the code? It's like, in many cases, the code's not available. In many cases, it's they ran the code once, they measured it, they said that the Earth is going to go, under certain assumptions, the average temperature of the Earth will rise 3 degrees, but I can't reproduce that myself. So it's a bit of a mess. There's spaghetti code, little code reuse, hard to debug. And then there's also the issue that many of my HPC friends don't believe, but it's really true, that in the HPC world, everything is about performance. And so there's kind of this culture, there's this attitude that if you only would work really hard and be a good boy or girl, you'd really get a lot of performance. You just have to roll up your sleeves, right? You get a whole lot of performance. And sometimes this kind of attitude is actually hurting global performance. You sort of make something faster for the moment, but then you sort of made it so obscure that you'll never be able to sort of work with it again, and somehow it's not quite the right way to even accomplish the very goal that the people want to do in that area. So I like this quote of Wittgenstein. So I really feel that in some sense, programming language, I mean, that's what we're here to talk about, has in many ways impaired the HPC world, and it's time for a change. And so I really do feel that the limits of the technical computing languages really mean the limits of the world. So talking about Julia, people talk about scientific multilinguals a lot. So all the time people say that we need computer scientists and people who care about the climate and mathematicians and software developers to be able to work together and interdisciplinary work and all that sort of thing. And I often find people saying, let's gather up teams to do these sorts of things. And very often these teams fail. They even fail to come together. The Julia community, however, is pretty fun and pretty exciting because in the Julia world, what we see is lots of people from lots of areas coming together and talking to each other and working together. And so The ability to be sort of multilingual in the Julia world is quite fun. So I think if I had to say what is the best thing about working in Julia for me, it's not the performance, it's not the ease of use. These are all wonderful things that we really enjoy, but it's the community. It's the people from all the areas that are actually literally working together. So I have this old slide. I think I'm going to pass by it quickly, but I always feel obliged to show it for 10 seconds. So there's a bunch of languages and some benchmarks. I don't even know if these are true anymore, but the ratio of time to see, and of course, I'm showing the slide, so Julia wins. All right, let me move on. So for the climate people, we talk about that writing that code is the new math, and there's kind of an attitude that I've been trying to articulate. I'm not sure I'm still doing a good job. Maybe you all can help me a little bit. But I sort of feel like when I talk to students, people feel that you learn math on a blackboard maybe, or maybe it's on PowerPoint slides nowadays. And then if you want to, like on the problem set, you code it up and make it live, right? So the math comes first on the blackboard, and then you code and as if it was sort of a byproduct, like a secondary thing. And more, I would like people to think of sort of the code as the math, right? As that it's not like, it's not this separate thing that comes later, right? But it's sort of the part of the whole process. And in the case, this is actually literally a piece of code that came from the climate model, the very little exercise that I was talking about last fall, where we got that factor of 3. So we started with some code. I mean, you can't read it. I just wanted to show you that there's like lots of lines of code. And then there was the LaTeX, which looked like this, right? And what we showed the folks what we showed the climate modelers was that you could actually write code that looks like this. It actually looks a lot like the math, and it works, right? And of course, what's happening beneath the surface is rather complicated, but at the highest level, you can write down the very kind of math that you want to do, right? There are these complicated integrals. You're figuring out something about pressure and temperature around the Earth, whatever the climate models are doing. But if you wanted to change your representation underneath now, you can, as opposed to what they were doing, which is hard coding a representation. So their code had a finite element model with specific elements. They had triangles today. If they wanted squares tomorrow, they wouldn't be able to have it, I think. Or maybe if they want to switch to a finite volume from a finite element, forget it. It's not going to happen. But of course, if you write your code with the right abstractions, you can then go underneath and sort of swap things out, right? And that's what abstractions can do. And again, I don't think for this community I would have so much to explain how important abstractions are, but for them it was quite a revelation. So the separation of the what from the how, that you can use abstraction layers to separate the what from the how. And in fact, I have this little story here. Here are some of the folks that I've been working with. The Tapio is at Caltech. Chris and Raphael and John are at MIT. And I was talking to them about abstractions, and I kind of realized there was a bit of a culture gap, because I had asked them, I said, they said, these climate people, you could even see, my climate sticker is down here, but I've got the Julia and the climate sticker on my laptop. But the climate, that's the project. It's being run out of Caltech, and the MIT part is the ocean model. The Caltech and some others are doing the atmospheric model. So they say, oh yeah, we use abstractions all the time. Matrices and vectors are our abstraction. And I'm saying, well, that's great. I like matrices and vectors myself, but that's not exactly an abstraction. I thought the real abstraction should be the function space that you're working on. And when we talked to them, I said we could do that. They said, you could do that with software? It was amazing to them that this was possible. Why didn't they teach me this in the first programming class? So people want to hear about abstractions. They want to be able to use it. And so it's kind of up to us, I guess, to teach people that. And when I started to talk to them some more and other people about abstraction layers, when I say that an abstraction can be, like if you have an array, say, and an array can be, I've got another slide that'll say this a little better in a minute, but if you have an array that can be a discretization of the Earth, it could also be on a GPU, or it could also be on a distributed computer. In other words, what I'm trying to say is, when people think of abstractions, they think of like a mathematical abstraction. They don't realize that changing your representation mathematically or changing it architecturally is really kind of the same thing in a way. And I'll say a little bit more about that, but that turned out to be a bit of a big deal. All right, so let me kind of, let's see. So, right. All right, so when we were getting into abstractions, of course, what everybody wants to do these days is machine learning, right? So that's still pretty hot. That hasn't changed, right? Like you say machine learning and people still look up. Is that right? You still looking up? Did you have a question or? So I think that worked. So as I'm sure everybody in this room would know, the neural networks of today are all run by optimizing and getting parameters. You optimize by running stochastic gradient descent is kind of the party line, I guess. And to get the stochastic gradient descent, you have to take derivatives. And so at the end of the day, a lot of machine learning tool changes these days are all about computing derivatives of things, right? So I've never seen so many derivatives taken in computer science in my history since the last few years. So everybody's taking derivatives these days. It's quite fun to see. So people talk about forward mode, reverse mode. People go up the tree, down the tree. It's kind of fun to watch, right? So reverse mode automatic differentiation is fast when there are many inputs, few outputs. People sort of build these things all the time. And I was listening to a lot of people explaining automatic differentiation, and I kind of had a little trouble understanding it in a way. Not that I didn't understand the detail, but it didn't seep in. So I thought I would share with you some abstractions that I was playing with and come back to Julia and show you how things just work, how abstractions just work with Julia. So I love matrices, by the way. So everything I turn everything into linear algebra that's my nail or hammer or whatever it is linear algebra. So the details of linear algebra won't matter, but the point that I'm making will matter. So if you're doing simple machine learning, for example, let me just start with scalars. So if what you're doing is you have some parameters that you're trying to optimize, and you have some nonlinear function, ReLU or something, whatever you might have, and you want to go ahead and automatically differentiate this, you could write the derivatives completely using matrices, right? And so here's a diagonal matrix. Here's the change to the intermediary variables. Here's the change to your parameters, and you get this simple linear algebra relationship. So if you want to solve this thing algebraically, you just write down here's the answer, right? This is sort of the matrix representation of the answer. And by the way, if you want to understand the difference between backward or the reverse mode or forward mode, the reverse mode says do this first and then multiply on the left by this matrix, right? The other mode, the forward mode, would be you do this first. This is a diagonal times the inverse of a matrix, and then you multiply by this vector, right? So that's the difference. And in any event, you could execute either way. You could do this in Julia pretty much with a backslash. All right, that's nice. I just changed notation and got the same thing that everybody else does with fancy matrices. But now, the next thing I want to do is not just do it for scalars, but do what's really done in the wild, which is this is done on arrays. So if you do this for arrays, what happens here's the arrays. What happens is those little entries of the matrix that started out just being scalars are now operators. In fact, here, let me just put the operators up. So you need these operators. See, when you think of matrices, you think of objects whose elements are numbers, right? Maybe later on you learn about block matrices or sparse matrices. Okay, and then when you get fancy, you realize that you could put other things as elements of matrices, including operators, right? Like in programming languages, it would probably be easy to imagine this. So the operators that are relevant for neural networks would be left multiplication by a matrix, right multiplication by a matrix, the Hadamard product or the element-wise product of a matrix. And so the representation that follows is that you need to solve this equation, but instead, this is a diagonal matrix of operators that are composed with each other. Okay? And here again, we have a lower triangular matrix with just one band of operators that are composed with each other. Well, the fun thing about Julia is that the very same code that would build matrices with scalars, you could put operators in and the code just works, right? And that is the beauty of abstraction. When you can reuse code you could reuse code in places when you never were expected to do it. That's the most wonderful thing that we can do. And in Julia, it just worked. And we're going to come out with a paper with this very soon. But basically, if you were familiar with languages, with a number of languages, the backslash is all you ever need to solve a linear system of equations. And in fact, that's all you need to be able to do that, right? So what's my point here? Abstractions. Abstractions give you reuse of code. Reuse of code gives you productivity, gives you so many useful things. Okay, let me kind of move on to, and so so we've even used that in some applications with the climate people. All right, let me move on to sort of another example from this I got from Valentin Chiravi and Tim Bizard. So Valentin's in my group at MIT, and Tim is at Julia Computing now. So coding on GPUs. So most of the folks that I know who work with GPUs for big science, what do? Some of them learn CUDA. You know, they're using NVIDIA chips, and they go for all the performance directly through CUDA if they can. And others use libraries that they just call libraries that use CUDA. Right? So those are kind of like the two main approaches. What we're doing with Julia, what Valentin and Tim and others are doing with Julia is basically saying that you want to be able to use this idea that I just showed you with the linear algebra. You want to be able to use low-level code, have it call GPU commands, the CUDA equivalents, middle-level code, high-level code. I mean, I've got sort of the whole picture that maps it out. But in the end, what's going on now, and I have some more slides I'll show you, is we can start to write regular Julia code without even thinking about GPUs. And little by little, we're starting to get these things to actually just work on GPUs. And you know, the situation is still a research problem in many ways, but that is the goal, that more people should be able to use distributed memory parallel computers, shared memory parallel computers, GPU computers, and not have to learn special new languages every time a new architecture would come out. We need the abstractions to be able to do the work for us. So I said I would explain this a little bit more, so here are some slides that do that. So in math, we have this. See, I'm in the math department, so I get to talk about math here. So in math, we talk about vector spaces, right? And if you might remember from your linear algebra days, or maybe you're hearing it for the first time, I don't know. But when you first see a vector, you see a column of numbers, right? And then you learn that you can add columns of numbers. So a vector space is an abstraction where you have a bunch of numbers, but they don't have to live in a column, and you can still add them. So for example, because you can add matrices, they form a vector space. They're not columns anymore. They're now two-dimensional, but they're still a form of vector space. Or you can add three-dimensional tensors, right? And so they form a vector space. Or for scientific applications, you could have numbers like a pressure and temperature on the middle of a widget. And since you could add those, they form a vector space. Or in the external field of an airplane, or as what's happening with the climate models, you could have temperature and pressure and so forth at various grid points along the Earth. Right? So every one of these form a vector space, which means that if I have numbers in each of these cells, I can add them, I can multiply by constants. We have inner products, usually well-defined as well, so we have a so-called inner product space. So, and linear operators can now be more abstract than just matrix times vector, right? Anytime, so for example, if I was on a two-dimensional grid and I wanted to create the operator that, like, at every point takes the average of its neighbors, right? That's a linear operator. You can represent it as a matrix in the traditional sense, but nobody on a computer ever would, right? So you can make it a sparse matrix, you can make it a dense matrix, but these are not the right, these may not be the right representations. The main point is that abstractly it's a linear operator, and that's the key thing. Now Julia is designed that if you've got an abstract array, you can do various operations. And so what's going on is we're able to get all of this code working on GPUs, or here's Here's Summit, which is sort of the, I guess still the fastest computer in the world at Oak Ridge. Because it's all the same abstraction, things still work without sort of extra layers of software. Okay, so let me think a little bit about timing. All right, so I'm going to get back a little bit more to that. Okay, so let me sort of, I broached upon machine learning, so let me tell you a little bit more about what kind of interesting machine learning things are going on in the Julia lab and in the Julia world. When we think about machine learning, much of the machine learning that people are talking about, I think is fair to describe as sort of the data-based machine learning. It's you get lots and lots of data. Ideally, you run it on some machine learning type something, and you find parameters to best fit your data in some way. Okay, and the scientists, the people who we work with, they're always asking, but do you get any insight out of this, right? So a lot of people are like, hey, it works, I don't care, it predicts what I want it to predict. But the scientists, they want to understand the real universe, and they're not really happy with the machine learning chains that exist today. So what's going on, let's see. Yeah, so what's going on is what people actually want to find ways to model real physical systems. And in any event, some of the things that you need to be able to do is differentiable programming or probabilistic programming. So here's the slide I really wanted to show you. So here's sort of the data kind of machine learning, right? And then there's sort of the end-to-end machine learning that we really need for physical systems. And so the concept here, and I'm sure in this group people hear about it, is the concept of software 2.0, where you basically say, give the behavior of a program, and if you write enough code, you'll be able to get what you want. So how can we achieve this? Well, this is sort of how things are happening in the world today with differentiable programming. You piece together pieces of various kinds, and if you want derivatives, you have to explicitly code it. So let me kind of see if I can make this point very clear. As I was learning about differentiable programming, I asked some folks, how could I take the derivative of a certain matrix operation? And I was told, oh, well, we don't do that right now, but you can teach it. What do you mean, teach it? Like, this is an automatic system. Why can't you just compute the derivative of this matrix operation? They said, oh, no, this matrix operation is calling a Fortran library. We're going to have to teach it. But once we teach it, it'll be fine. And that really opened my eyes to a bit of a problem with differentiable programming. If you have to teach it, then it's not automatic anymore, right? And so what works very nicely within Julia is the ability to go end-to-end between your application, your deep learning framework. Here I'm thinking of a numerical linear algebra library, but it could be any kind of library. What's really nice about Julia is that you can compose your software stack, and then you can reach back farther way down into your software stack and be able to do all kinds of operations that you'd like to do on your program. So you want to differentiate and so forth. So things just work, and we love that in the Julia world. So as I was talking about sort of physical-based machine learning, the kind that the climate scientists, I wanted to kind of bring this back to some of the folks that in computer science at MIT that people would talk about, which is why our building is so cold. So this was sort of the hot topic, literally, back last summer, back in June 2019. So the state is the name of the building where computer science CCL is housed. This is sort of a good example of sort of the difference between sort of a data-based machine learning and a physically based machine learning. So the data-driven approach, I guess, would be, I'm sort of making this up, but the data-driven approach was that, maybe you can add and subtract heat sources, put more space heaters or warm bodies or whatever you will, and measure the temperature changes, and then try to build a neural network to figure out where to place your heat sources. Sum the square difference from the desired temperature, and then ultimately try to figure that out. There's no physical knowledge of the universe when you do that. You just do a data-based approach. Okay, the physical model is the one where you would take, Fourier's heat equation, where you would literally, measure, you get the change in temperature based on, understanding the Laplacian of your situation. So if you have space heaters and whatnot, you'd be able to predict how the heat would flow throughout the room, right? So you see there's these different cultures, different worlds, and can we marry the two? And what's going on here is that we can, and this is work that Chris Rackauckas is really spearheading, is doing an amazing job. He's basically saying that you can put these two things together. He's building a lot of software to do neural ODEs. And the basic idea there, and you may have seen this in other places as well, but I think Chris has sort of really become quite the leader in doing this sorts of things. The idea is that in most machine learning tool chains, you've got this matrix W, these unknown parameters you're trying to optimize over. So you have the parameters are elements of a matrix. But who says that parameters have to be the elements of a matrix? Chris will tell you that the elements, the unknown parameters could be inside of other things, like inside a differential equation. Now, and so whatever it is that's unknown doesn't have to literally sit inside a matrix anymore, right? It could sit inside a differential equation. And then the beauty of that is then you can use the differential equations that are actually modeling your real situation. In this case, I'm talking about the flow of heat throughout a room, right? So you can actually use the real differential, you can use your knowledge of the physical world. You still might have some unknown parameters, and then you can use machine learning to get them. And so that's kind of the issue. But is this a computer science problem or an applied math problem? Well, I say that it's both. I've got another example of doing this that people seem to enjoy a lot. So the other word that sort of gets people awake is trebuchet. Well, you have to say that and people look up. It actually happened the other day at lunch. I heard somebody saying trebuchet, and I looked up. So we have a nice example, and Julie, if you ever want to just play with these sorts of things, there's the web page, but you could just Google this sort of thing, where you can use, you can actually, the trebuchet is a very simple example, but it kind of gets the idea across that, ultimately what you want to be able to do is set the angle and set the counterweight, and then, find out where where the thing is going to hit. And again, you could do it sort of by the data approach. You could, get yourself a trebuchet, I suppose, and then measure it, and keep having bigger and lighter boulders or something, and different counterweights, and throw at a thing and see where it lands. Or you could use the equations of gravity and see where things will fall. And so you can use the ODE solver. And so we have an example of that lots of people like to use. Okay, so this is sort of another thing that Chris Rackauckas is doing, so I'll talk about that. So this is another thing that sort of shows up a lot in the HPC world. So linear solvers. So linear solvers can be done directly through linear algebra packages, or it can be done iteratively. And in the HPC world, people say, oh, I have no problem solving linear systems. Just give me a black box that goes matrix times vector, and I could do any linear operator I want. I could have sparse matrices, structured matrices, whatever you want, and I'll be able to solve the system with things like conjugate gradient. Okay? Well, what Chris is doing, and this is sort of very interesting to me, is that he is basically being able to make the solutions of differential equations into a big black box. And so as long as you can add vectors and apply linear operators, he can solve differential equations now. And the beauty of that is that he has these codes. And the main reason I'm showing you these codes, they're not that exciting to look at, but I just want you to see that there's just multiplying vectors by a constant and adding it to another vector times a constant. It's sort of all over the place. But it's very, very simple vector operations. And as I said before, if your vector is a column of numbers, that's great. If your vector is a bunch of temperatures and pressures on the Earth, and by the way, they happen to be distributed on a parallel computer, or some of it's working on a GPU, it's fine. The code still works. It just works, right? And so now, I don't know, I think Chris Rackauckas has like 200 differential equation solver, and he tells me 165 of them are working without any extra changes nowadays. So and it's working its way towards all 200 or something. So this is what we're trying to get with code reuse. We're trying to get to get software that will just work on different kinds of hardware, that'll be practically useful for lots and lots of people. The other thing that Chris is doing, that's, he's sort of a busy guy. He does a lot of fun things. Another thing that he's working on is personalized medicine, where he's actually trying to figure out, apparently when you get a dosage of some medicine, you go to the doctor, he prescribes something, he or she prescribes something, you get a bit of a one-size-fits-all. I mean, you're lucky if there's sort of an adult and a child sort of dosage, maybe based on your weight a little bit or some other factors, but not much. But apparently, every human processes drugs very differently. And there's a differential equation that actually describes this processing, and Chris is working very hard on this. And in the end, there are these parameters that you have to machine learn through the differential equation. So that it keeps coming back, it's a recurring thing. And there's a lot of them, and you have to run hundreds of these things. And so Chris has this code, and you can run this with many, many different parameters, and these things just still work all the way down through Julia. And so that's kind of where a lot of the excitement in being able to run Julia for these sorts of things is coming from. All right, let's see. I've got a few more slides. Let me just mention them. We've got some stuff going on TPUs. So everybody's talking about heterogeneous computing, so distributed memory, GPUs, TPUs. So we're working, still lots of research problems, and happy to have other folks join us. We really need the help. I'm not saying that the HPC problem is solved by any means, but I think we've got our best shot at finally sort of having a language that can work for many purposes, including HPC. Here's the Celeste project, just to mention that's kind of another big HPC project. So in this project, the question was, it's a big machine learning problem. It sort of got Julia into the petaflop cub, which is a bit of a rare thing for a high-level language. And it was an application where people are learning the cataloging, essentially, the celestial skies. So that's another one. And then I'm going to come to a conclusion real fast. Here's the kind of the picture of the hotspots of Julia. Actually, I haven't looked at it. Let's see. Here we are in Greece. It looks like this is right here. So Julia keeps growing in terms of its use. There's several million downloads by now. We don't know. It's very hard to measure these things open source, but we know the various downloads that have happened. And let me just finish with one last slide here, which was someone pointed me to this blog that goes back to 2015 that I hadn't seen until relatively recently. And it's this blog by Brett Victor, who said that he's not really coding much in Julia. And he goes on and on about what can a technologist do about climate change, kind of a personal view. And you can go look at that blog yourself. And I was kind of surprised as you sort of go down and read a bunch of things about climate change itself. He does say that the best thing that you can do if you care about climate change, I mean, he wrote this, is contribute to Julia. So we would encourage that if you're interested. So I think with that, I'm going to conclude my talk. Jeff and Stefan will follow me right away, but let me stop right there.
We have some time for some questions. Yes. So you said you can have, for instance, you can specify your computations on like just an array, and then the array you would be able to move it to like some kind of hardware, to different types of hardware and things like that. Is the user in full control of where they go, and can you have like heterogeneous spreading? Like I could send some to one GPU and some somewhere else.
So yes, no, and maybe probably is the answer to your question. Mm-hmm. So let's see. So what can you do today, and what takes a little more work? One of the things that you can do today is set things up on a distributed memory computer, more or less. You can distribute things more or less any way you like as well. For the GPUs, what you do is you specify, in Julia the terminology is called a CU array, like a CUDA array, and it will place the data on the GPU and then will work on the GPU directly. So what the type system is basically how this is all done. So basically, depending on the type, this is where things go. I would love to see the way, maybe what I'm hearing from your question is to be able to do sort of arbitrary heterogeneity. And I guess the answer is, depending on how hard you want to work right now. But one can imagine sort of setting this up so that it could be, all the hooks, all the possibilities are there. I guess it's still a research project in various ways. But there's nothing stopping you from doing this sort of thing. So that's the yes, no, and the maybe.
Okay, thanks.
I have one flippant question, one serious one. The
Okay.
flippant one is, I met this guy, Nick Trefetten, and he claims to be the first paying customer of MATLAB.
Well, it happens he was my advisor, and he was the first paying customer.
Okay.
And what happened was, when it arrived with the plastic around it, he handed it to me.
I see. Okay, that resolves that question.
So he was the first paying customer, and I was the first user.
Sounds good. Okay.
So both are true.
Excellent. So the more serious question is I do a lot of things with manifolds, rotation groups, SC3.
I love
Euclidean.
manifolds.
So differentiation on manifolds, is there, do you do that with Julia? Can that be done?
So I haven't had, I wish I was doing it because I love this stuff. But sure, it can be done, and in particular, in the end, it's an abstraction, right? And so, and the math has been well established for, a few centuries on how to do this, and so one could do this. Now I know, I'm trying to remember, there was a group somewhere. I have to remember now where. There already is code that differentiation on manifolds that's out there, and I can't remember now who was doing it. But I remember a student of mine wanted to do it at one point, and then we spoke to some people. I'm blanking on who now, but it's out there. You can do it, and it's sort of it's just right.
Hi, and thank you for the nice presentation. So if I understood correctly, you are using Julia to run execute some models in high-performance computing to get statistics about how the climate is changing, right?
Well, I'm sort of like, my group is sort of the helper in that. Like, we love the fact that the real folks who are doing it are over in the EAPS department.
Okay.
We're doing the Julia part to keep them happy.
A question, have you tested how much more energy efficient, let's say, it's to run these models in Julia or in any other programming language?
So the only race is with Fortran and maybe C++, I don't know. So energy efficiency. So to be honest, these things are energy hogs. It's kind of a.
I know, that's why I'm asking.
It's kind of a.
Especially when you're running in a
it feels almost like a kind of like it feels hypocritical, right? You're running and wasting all this energy so that we can understand the climate change. So
since we try to find it, yes.
But way worse is all the machine learning tool chains that are running
some
right now
from
and
MIT and
killing the environment. I haven't done any particular calculation, but I'll share a story. This is not really answering your question, but it's a good story. So there was a computer company in the Boston area about maybe it was 10 years ago that was determined to show how energy efficient they could be. And they had this little stunt, and you can Google this, you could find this. They grabbed the MIT bicycle racing team, and they were actually in, I'll never forget this, they were right on the first floor of the Stata building, the one that you saw being covered in water in my slide. And they had the bicycle team, and they were trying to figure out, they were trying to set the record for, for gigaflops per kilowatt. And you could see them just, they weren't plugged into any wall, they were just biking away. So something we should be doing more of, perhaps.
Thank you.